This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you. The following is a continuation of a previous video which is available here and is highly recommended. For those of you who have seen the last video and simply want a refresher, we are looking for Ayn Rand's little stuff that exists where nothing isn't, and have been following guiding principles to get us there, and had acquired the following list of principles. Existence exists. A is A. Consciousness is conscious. The universe is causal. The universe is full. Nothing is prior to the little stuff. The laws of physics must look the same to one observer as they do to another, aka the principle of relativity. When we last left off, we were in the 1600s with Galileo Galilei, who had just given us that last principle of relativity in his book, Dialogues Concerning the Two Chief World Systems, through his observations of Jupiter and its moons. Within the same dialogues, Galileo also argued that light need not be instantaneous, but may actually have a finite velocity. But the closest Galileo could get to that velocity was that light had to travel at least 10 times faster than that of sound. However, research in astronomy, light, and natural philosophy were once again interrupted by the actions of the Church. The natural philosopher René Descartes had written in 1629 through to 1633 about the nature of the Aether and the solar system. However, it would not be published out of fear of the Church, and that what they had done to Galileo might be done to him. Descartes decided instead to rewrite this work by softening the heliocentric views. This softened version was compiled into a textbook called Principia Philosophiae, which Descartes wanted to have replace the Aristotelian textbooks which were taught at the universities at that time. The original copy eventually was published in 1664 in the book Treatise on the World and Light, or otherwise called The World. In Book 3 of Principia Philosophiae, under the title of The Observable Universe, Descartes states, "The only difference between my position and those of Copernicus and Tycho is that I don't attribute any motion to the earth." Descartes made a few arguments to demonstrate his case. The first being that the fixed stars are just like our sun, and are not fixed to the outer crystal spheres, but rather are the centers of their own planetary systems. Descartes states that each of these systems is filled with a fluid, openly dismissing the idea that the heavens are empty, and the motion of these fluids drag the bodies like planets in it. And the fluid eddies of the planetary system have smaller eddies, which explain the orbits of the moon around the Earth and the orbits of the followers of Jupiter, which were discovered by Galileo. Descartes expresses in this book the principle that Newton later takes as his own, and much later becomes known as Newton's first law of motion. Descartes expressed this first law in 1644 by stating that people tend to believe that motion requires actions, and therefore an object in motion requires an external force to continue said motion. But Descartes shows that that belief is caused by our atomized experience of life on a planet with gravity, and that the opposite is actually true, that it takes effort to prevent the body from moving down, including your arms, that the motion is ever present and we apply effort to stop ourselves from collapsing, and that we require effort to continue motion because of friction and gravity, otherwise we would remain in motion. Descartes saw this motion as intrinsic to the functioning of reality, and assumed that each natural element intrinsically moved at different speeds, such that fire element particles were intrinsically fast, and their quickness tore holes in slower objects which we see as burning or disintegrating. Air, earth, and water were naturally slower elements. Descartes held that the earth was trapped in this fluid and was itself at rest. The quick motion of the ether traps the atmosphere to the earth, and the motion of the air trapped the rocks to the ground, as rock is intrinsically stiller motion, and all is carried by the heavenly fluids. Quoting Descartes, "Let us assume that the earth is at rest, having no innate tendency to motion, because we don't see any such propensity. But let's not think that this prevents the earth from being carried along by the currents of the heaven, following the motion of the heaven without itself moving. Compare this with an unanchored ship that isn't driven by the wind or oars, floating motionlessly in the middle of the ocean, though it may be imperceptibly carried along by the ebbs and flows of the great mass of water. In this strict sense, the earth is not moving, nor are the other planets, because they are not transferred from the vicinity of those parts of the heaven which they are in immediate contact, insofar as these parts are considered as being at rest." Part 3. What the heck is light and ether, anyway? 4 years before the publication of Descartes' The World, the renowned natural philosopher and father of chemistry, Robert Boyle, was conducting experiments with a vacuum chamber and air pump which he invented. Boyle used his air pump to remove air from his vacuum chamber, to which he had placed a bell which could be struck inside the chamber. Boyle discovered that it was the air that allowed for the sound of the bell, as when the air was removed from the chamber, the striking of the bell would not produce a sound. The air can be removed from the chamber, which prevents the bell sound from having a medium to travel through. Therefore, sound requires a medium of air to exist. However, air was not clearly needed for light to travel. As the chamber was made of glass, and the bell was visible inside the chamber after the air was removed. Boyle concluded that light travels through a medium made of particles so much smaller than air that they can penetrate through the glass, unlike air, and therefore cannot be vacuumed out by his air pump. Boyle also experimented with magnetism with his vacuum chamber, placing a compass needle inside, and after evacuating the air from the chamber, a magnet was moved around the glass jar, which caused the compass needle to move. Therefore, light and magnetism, whatever they may be, can travel through solids like glass, but air cannot. So light and magnetism must be smaller than air. In 1665, Dr. Robert Hooke of the Royal Society and student of Robert Boyle published his book Micrographia, which mostly contains observations he made with his invention, the microscope. The book also contains some natural philosophical explanations of what the ether and light may be. Hooke considered light to be of an exceedingly quick but very small vibrative motion, possibly having the vibration perpendicular to the direction of propagation. Hooke's ether was similar to Descartes' in a few ways, and differed drastically in many other ways. Hooke thought if light was leaving stars in particular form, then stars would have to get smaller over time, as the amount of light particles leaving the stars would leave the star with no more fire element particles after a brief period of time. Hooke, being the man that gave us the spring equation, believed that light had to travel through the universe like a bunch of springs attached to each other, such that a motion of light physically traveled through the universe, but the restoring force of the spring would return energy to the source, and therefore would not deplete the stars. Descartes' ether had sent energy through the little stuff, like energy is transferred through tightly aligned billiard balls, such that no object moved but rather that light energy would just be the tendency to motion, whereas Hooke held that light itself was in motion. Hooke, being the student of Robert Boyle and main assistant to Boyle's experiment, had learned that sound is propagated by the medium of air, and so, like sound, light traveled in straight lines propagated in all directions with longitudinal spring-like motion, an idea that will be picked up by Christian Huygens some 30 years later, when Huygens describes light spreading in all directions in a series of waves in what he calls the luminiferous ether. Descartes provided an explanation of how the planets are forced to move in the direction of the ether vortex, as he believed that the ether, heavens, was composed of fluid matter, which was in motion. Boyle provided an explanation that the ether was composed of matter that must be very small as to penetrate all things, and Hooke provided explanations as to how he believed light was traveling through that ether. In 1676, Ole Romer provided an observation about the velocity of light, such that it was possible for him to predict a planetary event to the minute. Romer was observing the Galilean moons of Jupiter, and discovered that the moon Io had a constant, predictable orbit around Jupiter when watching it throughout the week or month. However, Romer found that when observing that constant velocity over the period of a year, the time it would take to arrive would shift back and forth between too early and too late. Romer realized that since Earth and Jupiter are in different elliptical orbits around the Sun, there would be points when Jupiter and Earth are as far apart as they can get. And there will be times when Jupiter and Earth are at their closest. The further away Jupiter was from the Earth, the longer it would take light reflecting off Io to reach Earth. And the closer Jupiter was to Earth, the quicker light would take to reach Earth. Romer found that light traveled at a velocity equal to about 22 minutes to span Earth's diameter, or about 220,000 kilometers per second, or about 136,701.66 miles per second. During the time period between 1665 and 1672, Isaac Newton was conducting research and teaching about optics. The former royal scientist of optics was Hooke, to whom Newton disagrees with both in the realm of physics and in a more personal way as well. Newton believed that light had to be corpuscular, and that color was based on the size of the particle, red light being of a greater mass size and speed, blue light being of a smaller mass size and a slower particle. Hooke believed that light was a spring-like pulse, and that color was based on the compression of the spring-like waves, having red light and blue light be a confused white light pulse, red being more compressed at the first and less compressed near the back, blue light less compressed wave followed by its more compressed part. This battle between Hooke's ideas and Newton's ideas would persist for hundreds of years. Newton argued that in order for light to travel in straight lines, such as when he made a pinhole light to enter his lab through a window curtain, and for light to reflect off of surfaces, light had to be made of particles. He rejected a dense fluid ether, and that light was a wave of the dense fluid medium itself, stating, quote, "A dense fluid can be of no use for explaining the phenomena of nature. The motions of the planets and comets being better explained without it. It serves only to disturb and retard the motions of those great bodies, and make the frame of nature languish. And therefore to make way for the regular and lasting motions of the planets and comets, it's necessary to empty the heavens of all matter, except perhaps some very thin vapors, steams, or effluvia." arising from the atmospheres of the Earth, planets, and comets, and from such an exceedingly rare ethereal medium as we described above. Newton also believed that if, according to Hooke, light consisted only in impressions propagated without actual motion, then in order for the sun to propagate light in every direction in an instant or in time, the light would have to bend into shadows as compressions in a fluid cannot propagate in right lines, and will bend and spread behind an obstacle, meaning the far side of Earth would see daylight bend around the planet, and it would light the sky at night. Newton also wrote that the vortex ether of Descartes and others doesn't account for the moons, as many moons around planets orbit against the supposed flow of the ether. Newton had no answer as to what the ether might be, and the only solution he provides in his book Optics is that God is capable of doing things we don't understand. However, what we got from Newton was that light can be described as a particle that is traveling through a medium. Newton's particles of light were based on the size of particles, and so despite his research on light reflection being quite solid and being the basis of optics, the corpusculars didn't have as solid of a basis for color and refraction as he had thought. Newton's hypothesis of light was not at all able to explain diffraction or polarization, and for this reason, some of the scientific community preferred Huygens' wave theory of light. Newton had attempted to explain a possible ether theory, but would later abandon it, stating that he did not feel a need to speculate on ether, as his math of the laws of gravity worked just fine without needing to explain the ether. Newton's universe thus sat nearly empty, but being somehow densely packed, but rare enough to not retard the planetary motion, hence why he abandoned explaining what it could be. Others rejected Newton's universe, as it suggested that things like gravity acted over vast distances without a direct causal link. Gravity is the word Newton coined from the Latin gravitas, meaning weight. This action at a distance problem would prevent a lot of scientists from accepting Newton's theory, as it was considered to be connected with Newton's attempts to bring occult agencies into physics, something Newton was known for. From the Greeks through to the classic natural philosophers like Descartes and Hooke, the ether was the most densely packed thing in the universe, and action at a distance was explained by causal physical collisions throughout the ether. So others saw Newton's action at a distance as impossible, as it would imply that a particle of light is traveling through literal nothingness, which would have only made sense to someone like Heraclitus. One of the scientists that did not believe Newton was the natural philosopher Christian Huygens, who, in 1690, published his book Treatise on Light. Huygens adopted a more Hooke-like hypothesis of the nature of the universe and light. Huygens assumed that light was just like sound, and that if the ether could be removed, light would vanish too. Huygens held that light was an effect caused by the disturbance of the ether, not a particle traveling through an ether or through nothingness itself. Huygens believed that light, like sound, spread out in spheres, and each ray of the sphere interacts with the medium particle which exists at every point in space, and this elastic billiard ball bumping spawns new spheres of elastic billiard ball bumping at those points in space, called wavelets. Light then is the effect of the elastic collisions of the ether. Another quick recap. Descartes said that space is filled with matter, which is vortexing around stars. He also stated in his theories on the nature of light that it was instantaneous, as is like being poked by a stick. Ether moves, light doesn't. Boyle said that the ether is filled with a subtle matter that explains both the lack of a vacuum and mechanical interactions like magnetism, and possibly other forces like gravity. Ether is stationary, light travels through the ether. Hooke, Boyle's student and assistant, said that the mechanical ether interaction may be like longitudinal spring-like waves, having gravity and other phenomena like light emitting in all directions from the source through the ether. Ether doesn't move, light is like a spring pulse. Newton originally believed that the ether was stationary and that the density of it got denser near a planet and rarer the further from the planet. But he changed his mind when he considered that the ether would still slow the motions of the planets, and that it may be possible that the ether is immaterial, a decision he left for his readers to decide. Ether unknown or doesn't exist. Light moves as a particle. Huygens had a different form of vortex theory, similar to Descartes in the sense that the vortex threw lighter matter to the edge, and gravity is the effect of the heavier matter being squeezed by the vortex. Huygens' change to the vortex theory was that light was the effect of a wave propagating through the ether. The Cartesian and Huygens theory can be said to be a vortex theory. Boyle and Hooke have a stationary ether, and Newton, though stating that not having an ether is absurd, his math didn't need one and spawned a purely mechanical motion of planets. Every form of wave theory or corpuscular debunking of wave theory was assumed that the waves were longitudinal waves like that of sound. In 1725, James Bradley conducted an experiment that was attempted by two other scientists on different occasions. The experiment was to measure the parallax of a fixed star in order to prove the Copernican model. The first attempt was done by Hooke, but Hooke's telescope did not have enough power to properly observe parallax. Hooke, however, left instructions in the failed experiment's paper, which could be followed to construct a telescope of sufficient power. The second attempt was conducted by Bradley's friend Samuel Molyneux, with Bradley helping him. However, Molyneux unfortunately died, and so in honor of his dear friend, Bradley made the third attempt at the experiment. All three men chose the same star, Gamma Draconis, the head of the Dragon constellation. The star was chosen for the reason that it never sets in England, the country of its measurement, and it passes directly overhead at some point of the day or night. Molyneux's telescope was built to Hooke's description, but Bradley had to have a smaller one constructed after Molyneux died in order to fit it into his observatory. The experiment was to detect stellar parallax, which is an apparent change in the position of a star due to the relative position of the Earth as it orbits the Sun. Bradley expected to find he would have to move his telescope in a circle as Earth circled the Sun, as that motion would make it look like the star is moving in a small circle. What Bradley found, however, was that he would have to move the telescope only half of the year. For one part of the year, the telescope had to be pointing slightly in one direction, hitting a maximum of 20 arcseconds. Then it would return back to 0 arcseconds 4 months later. Then, 4 months later again, he needed to move the telescope to a maximum of 20 arcseconds in the opposite direction. And again, 4 months later, it returned back to 0. And then 4 more, and back to the 20 arcseconds in the first direction. This observations of Bradley's was given a new term, called stellar aberration. And Bradley explained it with a simple analogy. If rain is falling straight down, a man standing still in the rain would see it fall straight down. And if the man jumps straight up and down, he will still see the rain fall straight down. But if the man walks perpendicular to the falling rain, he will have to tilt his umbrella in the direction of his motion in order to stay dry. This is caused by the same Galilean effect as dropping a cannonball from the mast. If the raindrop is 10 feet away when it is at eye level, and is at 0 feet away when it is at foot level, then it appears that the raindrop has moved towards you at a slope. You don't have to worry so much about the rain that is currently above your head, as it will be behind you before it can hit you. This also means that it is the velocity of the observer that causes this apparent position of the star, not the observer's position, which would have been parallax. In September, the Earth is moving at its most perpendicular to the parallel light rays of Gamma Draconis to the north, and the telescope needs to be tilted a tiny amount towards the north. To get an idea of the small amount of tilt, here is a 20 arc-second difference, and here is a degree difference. In December, Bradley's zenith is moving towards the star and is parallel with the light rays, and therefore the telescope can see the star at 0 arc-seconds from zenith. In March, the Earth is moving perpendicular, in the opposite direction it was from September, and the telescope needs to be tilted in the opposite direction from the September measurements. In June, the Earth is moving away, in parallel with the light rays, and the telescope can again see the star at 0 arc-seconds. Bradley explained the results of his experiments with the corpuscular theory of light, as the light was acting similar to raindrops falling. Using this idea, Bradley, in 1728, was able to make speed of light measurements, which were relatively close to the ones we know today. But more than that, Bradley discovered that the speed of light was a constant, as light from every star arrived at the same velocity. It may not seem like it today, but this discovery had profound implications. The idea that the speed of light didn't appear to change meant that the ether is stationary in the Earth's frame of reference, which is strange, as the Earth is always changing directions as it orbits the Sun. The effects of aberration will not be explained for another 200 years, and all those years are spent trying to explain how to fit stellar aberration into the other theories. Newtonian mechanics of planetary motion, however, was starting to demonstrate that Newtonian mechanics was not a totally accurate understanding of the universe. Just as today we know that Einstein's general theory of relativity must not be the whole picture, as it does not fit perfectly with quantum mechanics. And so too did the physicists of the 18th century come to realize that Newton's mechanics were great for small and close everyday equations, but they could not accurately explain planetary motion in what is famously called the three-body problem. Systems like the Sun, Earth, and Moon were not calculatable with Newton's mechanics, and attempts to use them provided the wrong answers. One of the scientists working on this problem was the prolific mathematician Leonhard Euler, who, in the years between 1744 and 1746, became an anti-Newtonian theorist, because of his work trying to use Newtonian mechanics. Euler eventually returned to the Cartesian vortex theory of the ether. However, the vortex theory predicted the motions of the planets would speed up, whereas the stationary ether theory predicted, as Newton suggested, that they would slow down the motions of the planet, and Euler had found that the Earth appeared to have lost a day since Ptolemy's observations of the changing length of a year. Euler also flipped Newton's ether idea, stating that the ether may be denser in space and rarer near the Earth and other bodies, making gravity an effect where we are pushed into the Earth as opposed to pulled or attracted into the planet. Euler never found a solution to what the ether was. However, his research into waves helped support his belief that gravity and other phenomena are caused by an impulse, as suggested by Hooke. Euler also took on Newton's optics, researching light and color, discovering that things like diffraction were better explained by light as a wave. Scientists like Augustin Jean Fresnel and George Stokes proposed alternative solutions to the reason why the speed of light did not seem to be affected by the ether. They assumed that there existed some form of ether drag, where the ether is dragged by the friction of the Earth when it is near the Earth, and has less or no drag in deep space. To understand this, let us return to the umbrella analogy. If the rain is falling straight down, and you are walking perpendicular to the falling rain, the rain would appear to be falling towards you at an angle. The ether dragging hypothesis would be analogous to the idea that as you walk, the air around you is dragged around you, such that when the rain gets close to you, it gets trapped in your local ether and is pushed by your ether wind. This explanation covers why Bradley may have had to tilt his telescope. If the ether is stationary and doesn't ever move, then the motion of the Earth should cause relativity effects, making the light appear to move at an angle as you move perpendicular to it, and straight down as you move parallel to it. However, this at all does not explain how the speed of light appeared to be constant. Thomas Young, in 1804, was one of the scientists that reasoned that light was a wave, and not a corpuscular as Bradley believed, and that the ether was immobile in the frame of reference of the sun, and that the Earth had no effect on the ether. But he could not explain the aberration effect. However, Young was able to show that light is a wave in other experiments. His most famous experiment was the double-slit experiment. If light was a wave like sound or water as they expected, then there ought to be an interference pattern when light moves past and through an object in its path. In the same way that a water wavefront hitting a double slit will cause there to be two circular wavefronts, so should light if it is a wave. Young demonstrated in 1803 that by shining a light through the double slit, there was in fact an interference pattern at the screen. Young also knew that light had to be a wave in order to explain why light reflects and refracts at the same time. If light was a single ball, then it could not do both at once. However, Newton had already demonstrated that the ether, which is what would be waving, cannot be doing so longitudinally, as this would cause the disturbance of the motions of the planets and would cause lighting effects that we do not observe. So it was, at the turn of the 19th century, that light had to be a wave. That wave had to be a wave in something, and that something cannot be a wave like sound. Also, light would have to behave like a particle sometimes. The ether would have to have been densely packed, but rare, transparent, fluid, but sometimes solid, frictionless, and also maybe having ether friction drag. The particle theorists at this time attacked Young in his inability to mathematically describe the interference pattern of the waves of light. They thought that they could explain diffraction with the idea that beads of light bounce off of each other and cancel. The particle theorists thought that they could finally kill the wave theory of light by holding a science contest on diffraction in 1818 at the Academy of Science. The winner of this contest would thus put an end to one of the two theories. Either the particle theory or the wave theory was going to emerge the sole victor. The winner of this contest was Augustin Jean Fresnel, whose paper supported the wave theory of light. Fresnel, without knowing much or anything at all about Huygens and Young, had already integrated their two theories into his own original work. Young, discovering Fresnel, suggested that Fresnel submit his paper to the Academy. Fresnel's idea could explain reflection, refraction, diffraction, and polarization, covering all of the topics that had been fought over for the last 200 years or more. One of the judges of the contest, Simon Denis Poisson, who was a particle theorist, thought that Fresnel's paper had a big issue. That being that the center of a circular shadow would have to have a constructive interference pattern, thus having a bright light spot in the center of a shadow, which he thought was ridiculous. One of the other judges and the head of the committee, Dominique Francois Jean Argot, took up the challenge on behalf of Fresnel and proved that the bright light spot does in fact exist as Poisson predicted. This was the end of the particle theory of light. The only thing that was an issue for the wave theory in the past was the longitudinal nature of the waves, but Fresnel ended that issue by proving that light is a transverse wave, not a longitudinal wave. This had a whole new effect on the theory of ether, as transverse waves cannot travel in fluids, but only in solids. It seems then at odds that the ether had to be a solid to allow light to travel, and yet it had to be a solid that doesn't affect the motions of planetary bodies, therefore returning us back to the issue of ether drag. Fresnel in 1830 came up with the math that would be used for predicting and measuring the ether drag by massive objects. For the next 50 years, the scientists battled it out over whether ether drag was occurring or not. In 1851, Armand Fizeau conducted an experiment with the first interferometer. He believed that the light will be dragged around by a medium, and so he uses columns of water flowing in different directions. Fizeau believed that his experiment demonstrated a partial ether drag, but his results were a lot lower than he had expected. A follow-up experiment by Hoek demonstrated that there was no dragging effect, and Hoek could not figure out why his version of Fizeau's experiment failed. In 1871, George Airy conducts an experiment as laid out by Young in 1804, using stellar aberration and a water-filled telescope. Airy concludes that the stellar aberration remains, and the ether drag could not be measured. In 1881 and 1887, Michelson, and later Michelson and his partner Morley, conduct the most famous ether dragging experiment, the Michelson-Morley interferometer experiment. The Michelson-Morley interferometer experiment found that light appears to move through the ether at the same velocity in every direction, no matter where the Earth is in its orbit, and no matter which way they rotated the experimental apparatus. This is where the conclusion that the ether doesn't exist comes from. But this experiment cannot disprove an ether, something that has to occupy space. This experiment merely showed that the ether was not being dragged. It proves that the luminiferous ether doesn't exist. That light doesn't need a material substance called a medium, like air, water, or glass, in order to travel. It proves that the little stuff which exists where nothing isn't is not a particulate matter. From this experiment, alongside Bradley's and Airy's experiments, we can add to our list of premises which cannot be contradicted. The ether is not a particulate matter. Light traveling through this non-particulate ether retains a constant velocity in all directions to all observers. Part 4. The ether is dead. Long live the ether. During this time between 1799 and 1887, scientists in different fields of physics were hard at work on electricity and magnetism. The invention of the voltaic pile in 1799, the first electric battery, allowed for the first time ever a steady continuous stream of electrical charge, which was thought to be a kind of fluid that flowed through the wire like water flows inside of a hollow tube. Before this continuous flow of electric fluid, it was demonstrated that static electricity can be used to reduce chemicals like tin, zinc, and antimony from their salts, which was something that was already known by alchemists, that fire will cause the transformation of matter in a process called calcination. The first productive use of this continuous flow of electrical fluid was used in chemistry experiments to reduce chemical compounds into their elements, as it was discovered by William Nicholson and Anthony Carlisle in May 1800 when their voltaic pile's two wires were placed in water. The water completed the circuit of the battery, and the two ends of the wire produced bubbles, which turned out to be the gases of oxygen and hydrogen. This discovery led scientists like Sir Humphrey Davy to use the voltaic pile to conduct chemical experiments, such as isolating, for the first time, chemical elements of calcium, strontium, barium, magnesium, and boron, as well as using the piles to create an arc lamp, the first incandescent light, which, despite our taking for granted view of light bulbs, was a huge deal, as this showed that there was some connection between electricity and light. That electrical sparks produced light sufficient enough to light a room. April 21st, 1820, Hans Christian Ørsted found that a magnetic compass needle was moved in the presence of the electric current, which was supplied by the voltaic pile. Ørsted had no clue what was occurring, simply that it was doing so in spiral circles around the wire, and also that they were in planes perpendicular to the wire. The effect strength depended both on how close to the wire it got and the magnitude of the current. That reversing the current reversed the compass needles, and that it penetrated all non-magnetic bodies, whereas it moved all magnetic bodies due to their resistance of the electrical conflict. This was the first connection between the two natural phenomena, and its publication caused an explosion of scientific discoveries. In fact, it is likely one of the most important discoveries in human history. Within weeks, André-Marie Ampère had already developed Ørsted's discovery into a mathematical formulation on electrical and magnetic interaction, and later formed Ampere's force law, which describes the production of mechanical force by the interaction between the electrical current and the magnetic effect related to it. This inspired Humphrey Davy and William Wollaston to attempt to use the electric current and the magnetic effect to create a mechanical action, otherwise called an electrical motor. But the pair failed due to the fact that they thought the circular magnetic effects were spiraling along the wire. Davy's student, Michael Faraday, in 1821, picking up the pieces of his supervisors, discovered that the circular effect was not spiraling up the wire, but rather that it was more like a set of enclosed cylinders around the wire, which allowed him to create the first electrical motor. In fact, he created two. In 1825, British electrical engineer William Sturgeon invents the electromagnet, a horseshoe-shaped bar of iron with a loosely wrapped coil of copper around it. When a current was run through the copper coil, the magnetic effect of the currents were somehow given to the iron bar, such that the bar, when the current is flowing, becomes a super strong magnet, and stops when the current stops. Faraday, in the summer of 1831, used this electromagnetic idea of coiling wires around iron, and wrapped a wire around one side of an iron ring, and another wire to the opposite side of the iron ring. One wire was connected to a battery, the other to a galvanometer. Faraday discovered that the galvanometer's arm would move briefly when the current was turned on or when the current was turned off. The current had induced a current in the second coil. To Faraday, this meant that there was some sort of tension in the state. To better understand what was happening, Faraday experimented with a permanent magnet instead of an electromagnet, and found that he could move the needle like that of the last experiment by moving the permanent magnet in and out of the coil of wire. The motion of the magnet past the coil caused or induced a current in the wire. Faraday knew that magnetic forces could be seen with the use of iron filings, and he used this visual of the lines of force to show the law that the magnitude of the current is dependent upon the number of lines of force that pass through the conductor in a unit of time. Faraday then quickly followed that discovery with the idea that a continuous stream of electric current can be produced by the spinning of a copper disc between the poles of a powerful magnet. This dynamo was the first design of the electric motor that we use for just about everything every day. Faraday, being of a lower class and having gained all his learning from books he binded as a bookbinder, was either unwilling or put down for his speculative ideas, and did not tend to share them with other scientists, except for his supervisor Davies and a few others. However, on April 11th, 1846, a colleague of Faraday's was to give a lecture at the Royal Institute in London. But he had terrible stage fright, and at the last moment panicked and ran out into the streets, leaving Faraday to cover him. Unprepared, Faraday briefly discussed his speculative theory of the lines of force. These speculations caused a great stir in the community, but as Faraday did not have the mathematical skills to back up his claims, most people did not follow through with his speculations. Faraday had received a request to convey his speculations by a one Richard Phillips, Esquire. The letter Faraday wrote to Mr. Phillips was titled, Thoughts on Ray Vibrations. In this endeavor to explain himself, Faraday writes, quote, The point intended to be set forth for the consideration of the hearers was, whether it was not possible that the vibrations which in a certain theory are assumed to account for the radiation in radiant phenomena may not occur in lines of force which connect particles and, consequently, masses of matter together, a notion which, as far as it is admitted, will displace with the ether which, in another view, is supposed to be the medium in which these vibrations take place. Perhaps I am in error in thinking the idea generally formed of the ether is that its nuclei are almost infinitely small, and that such force as it has, namely its elasticity, is almost infinitely intense. But if such be the received notion, then what is left in the ether but force, or centers of forces? As gravitation and solidity do not belong to it, perhaps many may admit this conclusion. But what are gravitation and solidity? Certainly not the weight and contact of the abstract nuclei. The one is the consequence of the attractive force, which can act at distances as great as the mind of man can estimate or conceive, and the other is the consequence of the repulsive force, which forbids forever the contact or touch of any two nuclei. So that these powers or properties should not in any degree lead those persons who conceive of the ether as a thing consisting of force only, to think any otherwise of ponderable matter, except that it has more and other forces associated with it than the ether has. It may be asked, what lines of force are there in nature which are fitted to convey such an action and supply for the vibrating theory the place of the ether? I do not pretend to answer this question with any confidence. All I can say is that I do not perceive in any part of space, whether to use the common phrase, vacant or filled with matter, anything but forces in the lines in which they are exerted. The lines of weight or gravitating force are, certainly, extensive enough to answer in this respect any demand made upon them by radiant phenomena. And so, probably are lines of magnetic forces. And then, who can forget that Monsanti has shown that gravitation, agration, electric force, and electrochemical action may all have one common connection or origin, and so, in their actions at a distance, may have in common that infinite scope which some of these actions are known to possess. The ether is assumed as pervading all bodies as well as space. In this view now set forth, it is the forces of the atomic centers which pervade and make all bodies, and also penetrate all space. As regards space, the difference is that the ether presents successful parts of centers of action, and the present supposition only lines of action. As regards matter, the difference is that the ether lies between the particles, and so carries on the vibrations, whilst as respects the supposition, it is by the lines of force between the centers of the particles that the vibration is continued. As to the difference in intensity of action within matter under the two views, I suppose it will be very difficult to draw any conclusion. For when we take the simplest state of common matter, and that which most nearly causes it to approximate to the conditions of the ether, namely the state of the rare gas, how soon do we find in its elasticity and the mutual repulsions of its particles a departure from the law, that the action is inversely as the square of the distance. In 1849, William Thomas, commonly known as Lord Kelvin, in a letter to Faraday, explained mathematically how Faraday's predicted magnetic fields should affect the plane of polarized light. This led Faraday to reattempt his old experiments and was able to prove that magnetism and light are related in what has come to be known as the Faraday effect, which in simple terms demonstrates that a magnetic field can be used to rotate a polarized light, or even more simply put, a magnetic field can control light. In 1852, Faraday wrote a paper entitled On the Physical Characteristic of the Lines of Magnetic Force, in which he cautiously shares his speculative philosophy on what he called force lines and their role in the process of action at a distance. The scientists and philosophers of the last 2,000 years were attempting to get rid of this action at a distance, using the ether as some sort of mechanism, which was getting more and more complex. By this time, Faraday had held an entirely different view of that ether, no longer believing, like the others, that it was composed of particulate matter, but rather that the ether was the field which was capable of supporting the tension of electricity and magnetism's lines of force. The work of Faraday led to the work of James Clerk Maxwell. 14 years before the famous Michelson-Morley experiment conclusion, in 1873, James Clerk Maxwell had just completed his treatise on electricity and magnetism. Maxwell's treatise refrained from making claims about the ether, stating within, quote, "These and many other phenomena of electrical discharge are exceedingly important, and when they are better understood, they will probably throw great light on the nature of electricity as well as the nature of gases and of the medium pervading space. At present, however, they must be considered outside the domain of the mathematical theory of electricity." Maxwell, like Faraday and Newton before him, did not want to lose the facts of reality to speculations on the ether, and therefore none of them came to anything but physical truths to construct their mathematical formulations. All of Maxwell's equations are derived from physical observations, and the equations explain how the fields of force are constructed as demonstrated by the physical experiments that defined them. The addition of the Lorentz force law completed the understanding, as the force law explains how these fields will affect the things within them. Maxwell therefore showed how objects in the field create forces, and how those forces would in turn affect the objects in the field. Let us get a better idea of what a field is. A field is an abstract idea that says there can be assigned a value for each point in space and time. This value represents some physical quantity. For example, we can take a room and divide it up into imaginary boxes of equal volume. Say each box is 1 cubic foot, meaning extends 1 foot east to west, extends 1 foot north to west, and extends 1 foot ground to ceiling. If the room is 1,000 cubic feet, 10 feet in each direction, then there are 1,000 imaginary boxes stacked 10 by 10 by 10. This room can be said to become a field when we put a thermometer inside every box. The field in this case would be a scalar temperature field. The values at each point in the space of the room would be the temperature at that specific location, and those temperature readings would change over time. We can also stick other measuring devices in each box, like a gravity detector, an electromagnetic detector, a photon detector, a wind speed detector, and so on. Each of these detectors would register some physical quantity, which is the result of having received energy from the environment. The field of forces of gravity would have vectors which point in the direction of the Earth. The electromagnetic detector would register some electric and magnetic fields of force, etc. The fields, then, are just our way of dividing up space and time so that we can understand what each point in space and time is experiencing at any given moment. Faraday's lines of force require time to propagate, and Maxwell helps explain this with a real example. An electric current can cause a magnetic field to appear, but it doesn't have to be an electric current. A time-varying electric field, a short vibration in the electric field, can also cause a time-varying magnetic field, a short vibration in the magnetic field. And a time-varying magnetic field can cause a time-varying electric field. And this self-propagating electromagnetic field can be written as a wave equation, and the speed of this wave happens to be the same as the speed of light. Leading to the conclusion, quote, "The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws." From this, we can conclude that light is an electromagnetic energy disturbance in the electromagnetic field. Conclusion: that which exists where nothing isn't. The little stuff is that which is where nothing isn't. It fills the universe and can be otherwise called the ether. The ether, if it had the ability to do so, might wish to quote Mark Twain to say, "The reports of my death have been greatly exaggerated. The ether is alive and well despite the claims to the contrary." Today, that ether has taken on the name fields or even space-time. The little stuff is not particulate, but that was never a requirement for Ayn Rand or Leonard Peikoff. All that was philosophically necessary was that something exists where nothing isn't. Today, we know that light is a packet of energy, an electromagnetic disturbance in an electromagnetic field, and that its speed is a result of its nature as a massless energy chain reaction of time-varying oscillations in the ether. We have walked through the history of the ether and have come out on the other side having learned that the ether didn't die. The bad ideas about it died, and what was left standing has led to the marvels of the world around us today. The physics of field theory, which has grown from this discovery of this new ether, has advanced science and technology tenfold, if not more, much, much more. With the aid of guiding principles, we have shown this case for Ayn Rand's little stuff has a solid foundation in physics. Next time, we will take what we have learned about the ether and light and explore the consequences of this new ether. We will examine what Einstein has to say about Maxwell's electrodynamics Galilean relativity problem, and why that demonstrates the case for the special theory of relativity. Until next time, I have been your host, Ryan Cooney of Existence University. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.